Hello again. This is Math 2245 coming to you from the College of DuPage, and the title of this lecture is Determinants 1. Please be attentive learners while watching this video. By way of introduction, you have studied determinants before, but mostly what you focused on was not the formal definition of the determinant, but how do you compute determinants, and you might have learned different ways of doing it. We're going to go in more depth here, and we're going to begin with the definition of the determinant and the rigorous mathematical definition of the determinant. It might be something you haven't seen before. So we're going to talk about the determinant function. This is not such an easy thing, and it involves some ideas and notation that you might not have run across, so we're going to actually define the determinant function. We need to get some preliminaries out of the way first. So, first, a permutation of a set of integers is an arrangement of all the integers in a list without omission or repetition. So a permutation of 1, 2, up to n will typically be denoted by I1, I2, ... all the way up to In, where I sub 1 is the first number in the permutation, I sub 2 is the second, and so on and so forth. So, example 1, let's list all permutations of 1 and 2. Well, if you have the set 1 and 2, either you can have 1 come first, followed by 2, or 2 come first, followed by 1. That's not too bad, is it? Now let's talk about 1, 2, 3. Well, there are 3 ways that we can have the first number, that is 1, 2, and 3. And once we've picked that, there are 2 ways we can have the second, and 1 way we can have the third. And so we will get 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Now that can sometimes be difficult to find all the permutations if there's more than 3 numbers, but you can make a tree like I showed you here, and that can get you all the things. At the top of all, we list the numbers on the list, and then from this top number we branch out with each of the remaining numbers. At the second number we'll again branch out with each of those numbers, and so on and so forth. Then each branch will represent a permutation of the given numbers, or you can see that the six permutations up here are represented by these graphs. As you can see, the number of permutations for a list will grow quickly as we add numbers to the list. In fact, it can be shown quite easily that there are n factorial permutations of the list 1 through n for any list containing indistinct numbers, and we're often going to be working with this list, so realize that there are n permutations associated with this. Now we're also going to talk about things called inversions in permutations. An inversion will occur in the permutation I1, I2, up to In whenever a larger number precedes a smaller number. Note as well, we don't mean that the smaller number is immediately to the left of a larger number, but anywhere to the right of a larger number. So just to practice this idea of inversion, let's look at determining the number of inversions in each of the following permutations. Okay, so let's start with the first one, 3, 1, 4, 2. So we will have 2 inversions associated with the 3. We'll have 0 inversions associated with the 1, and we will have 1 inversion associated with the 4. Again, we're going to the right. In the first case, there are 2 numbers to the right of 3 that are smaller. Let's do this again. Let's do this in detail. For the first one, the remaining ones you can do much quicker. So what we're going to do is we're going to mark the number we're looking at in red, and to the right give the number of inversions for that particular number. So 3, you can see that there's 2 inversions because 1 and 2 should be on the other side of 3. Now for 1, there are 0 inversions because 4 and 2 are both bigger than 1. And for the 4, there is 1 inversion. So in this case, there are 2 numbers to the right of 3 that are smaller than 3. So there are 2 inversions there. In the second, we're looking at the smaller number in the list, and so we won't have any inversions there. And then with 4, there's 1 number to the right, and that is smaller than 4, so pick up another inversion. Now there's no reason to look at the last number in the permutation since there are no numbers to the right, and so we won't introduce any inversions. So this has a total of 3 inversions, and that's how we get it. Let's look at the next one, 1, 2, 4, 3. We'll do this much quicker. Think about it. There are 0, 0, 1 inversions in this. Note that the number in the sum above represents the number of inversions for the number in that position in the permutation. Let's look at this one. So with the 4 there are 3, with the 3 there are 2, with the 2 there is 1. So there are 6 inversions in that one. For this one, there are no inversions because everything is in the correct order. And in this one, associated with the 2, there is 1 inversion, that's with the 1. For the 5, there are 3. All 3 of these numbers really should come before 5. For the 4, there are 2 and 0 for a total of 6 in this one. Now, next realize that a permutation is called even if the number of inversions is even and odd if the number of inversions is odd. Okay, so let's classify as even or odd all the permutations of the following 2 lists, A and B. Okay, well if you look at this, what you will see is that there are 0 inversions with the first permutation, and there's 1 inversion in the second, so those are even and odd. Let's do the same thing with the 6 that we have for part B. And we find even, odd, odd, even, and odd. Now, suppose we have an n by n matrix, and we are approaching having the definition of the determinant, but not yet. So suppose we have an n by n matrix. Then an elementary product from this matrix, this is the definition, will be a product of n entries from A, and none of the entries in the product can be from the same row or the same column. So find all elementary products for a 2 by 2 matrix and for a 3 by 3 matrix. Well, for the 2 by 2, and the easiest way to think about that is to say, well, each elementary operations will contain 2 terms, and each term must come from a different row. So we know that each elementary product must have the form A1 blank and A2 blank, and I fill these in with the numbers that come from a permutation. So the elementary products for a 2 by 2 matrix are A11, A12, A12, A21. And for a 3 by 3 matrix, again, we start with this, but each elementary product in this case will involve 3 terms. And again, since all must come from different rows, we can again write down the formulas they must take. So does A1 blank, A2 blank, and A3 blank. So the 3 elementary products are A11, A22, A33, and the others that you see here. Now, for a general n by n matrix, we will have n factorial elementary products of the form that look like this. A1, I1, A2, I2, all the way through AN, IN, where I1, I2 up to in ranges over all the permutations that we have of that. These numbers can get very big very fast. Now we can take care of the final preliminary definition we need for the determinant function. A signed elementary product from A will be an elementary product A1, I1, A2, I2, all the way through AN, IN. This is multiplied by a plus 1 if I1, I2 up to IN is an even permutation, or multiplied by a minus 1 if I1, I2 all the way up through IN is an odd permutation. Or you could think about this as minus 1 raised to an even power, or minus 1 raised to an odd power. Okay, so let's return and look at the 2 by 2 matrix and 3 by 3 matrix and find all the signed elementary products for these. Okay, let's start with the 2 by 2, and you can see that what we get is A1, 1, A1, 2, which is positive, and a negative A1, 2, A2, 1. Similarly, for the 3 by 3, we have 6, and we get the signs in these fashions. Please check to make sure you understand that. And now we're ready to give the definition of the determinant function. If A is a square matrix and the determinant is only defined for square matrices, then the determinant function is denoted by det, or det of A is defined to be the sum of all signed elementary matrices of A. Note that we will often call this number DETA the determinant of A. Also, there is different notation. Sometimes it's shown as an absolute value, and in fact, I think in our book frequently it is. And so we'll say the absolute value of A, but that really means the determinant of A. It'll be clear from the context, and often we'll write those bars and just put the entries of the matrix in there. So this is the matrix that we have been calling A. So now that we have the definition in hand, we can start writing down some formulas. Let's give a formula for the 2 by 2 and 3 by 3 matrices. And we're only going to do those because for any matrix larger, the formula becomes very long, messy, and those sizes there are alternate methods for computing determinants that will be easier, and we will prove many of these. So with that said, we've got all the signed elementary matrix for the 2 by 2 and 3 by 3 matrix, so we can just write them down. For a 2 by 2 then, the determinant of A, also denoted this way, is A11 times A22 minus A12 minus A21. And the determinant for a 3 by 3, the determinant of A, is going to be these 6 sums. And notice the signs are there. But already with the 3 by 3, you can say it's messy and it's not so fun to memorize. And there is a way that you might have studied in high school to calculate these and remember these more easily. With the matrix A, we will take the green products minus the red products. For the 3 by 3, what we'll do is we'll repeat the first 2 rows, and we'll take the green products and then we will subtract the red products. So let's practice this in this example 7. Please pause the video and try to do these, and let's see how you did. Well, for A, it's pretty simple to discuss. It's 3 times 5 minus, and then it's 2 times a minus 9. You get 33. For B, we repeat the columns, and we go the green products, adding them together, minus the red products, and we get minus 467. Finally, for example C, we will get 0. So what you've seen is that the determinants of matrices can be positive, negative, or 0. And remember, there are no quick memorization techniques for computing determinants for matrices larger than 3 by 3, although we will talk about how to do those and prove some theorems about those. So what we're going to be doing subsequent to this is we're going to take a look at properties of determinants, some different ways of computing them, and an application of determinants. So some good stuff to look forward to. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself. Self-care is important, and of each other, because we're all in this together. God bless you all.